Okay, so good afternoon, everybody. My name is Jorge Garcia, and in next few minutes, I will talk about my work on pairwise velocities in the strongly nonlinear regime using n-body simulations from models beyond lambda CDM. So let's start by a very short motivation. Redshift space distortions is among the most powerful proofs for gravity theories. What we have here is just a picture of the two-dimensional correlation function, just to show the two important effects. One in the nonlinear regime, the so-called fingers of God, where the velocities of the cosmic tracers exceed the Hubble flow, and on larger scale, we have the Kaiser effect. Both distortions, both effects are dynamical distortions, and there they contain valuable cosmological information. Therefore, by constraining, by modeling the redshift space distortions, we can extract this information, like such as the growth rate parameter. A simple approach to model the redshift space distortions contains at least three ingredients: a description of the nonlinear power spectrum, a description of the pairwise velocities, and the dispersion of the velocities. For these three ingredients, one can adopt a host of prescriptions. The nonlinear power spectrum can be computed from a halo model, from a halo approach. The V12, the pairwise velocity, can be computed from also a halo approach and standard perturbation theory, like one loop standard perturbation theory, as well as the velocity dispersion. In this work, we are focused on the modeling of the pairwise velocities, V12, and here we have that in a first approach, the pairwise velocities are related to the density field following this expression that is valid. It comes from a pair conservation, from conservation laws, and is more or less valid for the regime that is shown in this figure, that in configuration space is equivalent from a few megaparsecs up to 40 megaparsecs in our work. So we can also extrapolate the linear regime to the nonlinear regime using this kind of parametrization. Here, the bar correlation function is related to the volume, actually is the volume average correlation function, while this alpha parameter is related to the slope of the correlation function. There are also some linear approximations for V12. In all cases, for the linear approximations, it is proportional to the Hubble parameter and the growth rate multiplied by the correlation function or its volume average. This is the definition that we use to compute the V12 from our simulations, considering that we have access to all the velocities and also the positions, and also the definition of our coordinate system and the line of sight definition. The dynamical range that we consider is between 6 megaparsecs up to 43. Let me introduce briefly the set of n-body simulations that we employed. Here we have a simulation for GR, and we consider also two models of modified gravity. Those that are here labeled with the letter F, they correspond to the Husavitsky FoF model for two different amplitudes of the modification of gravity, and the ones that are labeled with the letter N, they correspond to the normal branch of the DGP model, the N1 and the N5. The upper panels, they show the distribution of halos, while the lower panels correspond to a population of galaxies. The triangles, they correspond to the distribution in real space, as we have here. The lower triangles and the upper triangle, they correspond to the mapping in redshift space. The simulations, they correspond WMAP cosmology in a box of 1 gigaparsec with about 1,000 million dark matter particles for 4 different redshifts, with a minimum mass as indicated here, 8 times 10 to the 11 solar masses. So we test for all those simulations the different prescriptions that I commented before for the pairwise velocities. Here we have a first result. The black line is the result for GR and redshift 0 from our simulations, while the color lines, they correspond to the different linear approximations. We can see that this one, the pink one, that actually corresponds to this equation, covers widely the dynamical range, while the other equations, they agree well, at higher scales. So then, since we are interested in the behavior at the smaller scales, we use also alophyt as an input in the pair conservation that we have here, and we can see that the results, it's much better. It's represented here by the green line. So alophyt provides by far the best approximation, since it covers the entire dynamical range. The red line, instead, is the prediction by CLPT, by the convoluted Lagrangian perturbation theory. So what we have now here is the results in clustering in real space for each one of the model. We plot here only the relative difference. Upper panel for the V12, the velocities, lower panel for the correlation function. So for the first model, for the FOFR5, the Husavitsky 5, we have that in the velocities, there is a difference with respect to lambda CDM of about 10%. However, in the clustering, when in the correlation function, this is diluted and it's about 3%. We can see also that for higher scales, beyond the 20 megaparsecs, this model is not possible to distinguish it from the standard scenario below 5%. Now for the F6 model, for the FOFR6, we see that is degenerated for the entire range that we consider, both for the velocities and for the correlation function. The difference are about 1%. For the NDGP1, the signal is quite constant in the entire range, and it has about 20% of difference with respect to lambda CDM in the velocities and 50% with respect to the correlation function for GR. The last one is the NDGP5 that behaves similarly to the previous one, to the NDGP1. It has a constant signal for both the velocity and the correlation function here, but the amplitude is smaller, about 5%. The fact that the signal is quite constant, it can be related to the screening mechanism of this model. It's also important to measure that for the very small scales below about 6 megaparsecs, we cannot trust in those results, since the results are out of the range of validity of halophyt. So now let's move to the redshift space in order to extract some cosmological parameters, the growth rate factor. We measure the two-dimensional correlation function for all the models. We use distant observer approximation, and also we projected the two-dimensional correlation function onto one-dimensional statistics using a Legend expansion, as we can see here. So from here, we can obtain some constraints of the growth rate, especially when we don't have a bias parameter. In the case of pure dark matter samples, we can recover the growth rate, but when we consider the halo samples, we constrain instead the beta parameter, the linear distortion parameter that contains mixed information of both the growth rate and a linear bias. We can see here some results of those constraints. I would like to conclude saying that we analyze the dynamics of the pairwise motion with the prediction of the convoluted Lagrangian perturbation theory approach and with approximated expressions for the linear regime. A proper modeling of the pairwise velocities provides a means to untangle the screening mechanisms of the modified gravity. In the case of the FOFR 6 and the MDGP 5. Modified gravity models with a weaker screening mechanism, like the MDGP 1, can be clearly differentiated from GR at all scales. The clustering signature of FOFR model F5 strongly degenerates with lambda CDM, as well with N1 and F6 for all the scales that we consider. However, the amplitude of the pairwise velocities for F5 has a significant signature about 5% for distance below 20 megaparsecs. The analysis of the pairwise velocities promise to be less susceptible to the growth rate bias degeneracy, as revealed by our analysis using n-body simulations. However, a robust study based on high-resolution simulations for each modified gravity model is needed to chart the growth rate bias degeneracy and to add such modeling to derive the F sigma 8. I'm concluding here. Thank you very much for your attention.
Thank you, Jorge. Nice talk. We have some questions from the audience or from the chat. I remind you that the discussions can continue on the Discord server, just in case. Okay, we have one question here in the audience.
Yesterday we had a talk about the effects of baryons on this kind of measurement. So, what your opinion would change the difference, including baryons?
Yeah, thank you very much for the question. It is very important because that's the next step in our research. We need, since we are considering middle nonlinear scales, the effect of baryon is quite important. So indeed, there is also a degeneracy between the F sigma 8 when consider modified gravity, and also when we consider baryon. So indeed, we need to move to hydro simulations and to see what's the effect, because we know that there is a impact in those constraints, also including not only baryons but the effect of massive neutrinos, that even if we are working with a small scale, the effect of massive neutrinos is also degenerated in the scales that we are considering. So yes, the answer is yes. We need to perform a better modeling of our power spectrum. That is the key ingredient in the modeling.
Any other questions? Okay, we can thank Jorge again. Thank you for the talk.
Okay, thank you very much.